and the management of UILISA. Dr. Sherifat, please, you can take over.
Hello, everyone. It's good to have you all here. Like Mr. Bosa Robert has said, I'm Sherifat Follow by name. I'm administrative coordinator of UILISA. By UILISA, it is University of Ibadan Laboratory for Interdisciplinary Statistical Analysis, which is a member of the LISANet that is situated in the University of Colorado, Department of Applied Mathematics and Statistics, Colorado, USA. And our presenter today is one of us. Presently, it's now in the United States of America, which is Dr. Kazeem Adepoju. And let me quickly read a citation. Dr. Kazeem Adepoju is currently a lecturer at the School of Statistics, University of Minnesota, USA, and an assistant professor of mathematics at the North Central University, Minneapolis, USA, and an instructor in Mathematics of Plymouth, USA. He was formerly a lecturer at the University of Ibadan, Nigeria. He is also a member of UILISA team. He attained a professional diploma in statistics with distinction. He got his Bachelor of Science in Statistics with a first-class honor, Master of Science, as well as PhD in Statistics, all from the University of Ibadan, Nigeria. Dr. Kazeem did a postdoc under the watchful eyes of Professor Kenneth Jones, the director of the School of Statistics, University of Minnesota, United States of America. Dr. Adepoju's research interests include mathematics, statistics, robust statistical method, statistics education, random effect estimation in repeated layout setting, and modeling longitudinal data. He has presented in a good number of international conferences around the world and has published more than 30 research articles in a scholarly journal. He is a member of Nigerian Statistical Association, NSA, Nigerian Mathematical Society, American Mathematical Society, Mathematical Association of America, Minority Society of Mathematical Societies and Probability, and American Statistical Association. Dr. Adepoju is from Alafara Olubadi Compound, Ibadan, Oyo State, Nigeria, but was raised in Ondo State, southwestern Nigeria. He is happily married to Nurat Adepoju and blessed with 5 lovely daughters. Permit me to welcome Dr. Kazeem Adepoju to present his. Dr. Adepoju, you are welcome.
Okay. Good day, everyone. I first want to confirm if everyone is hearing me clearly. Are you hearing me clearly?
Yes, we can hear you. It's very clear and loud.
Thank you so much.
Very well.
I want to welcome everyone to my talk today. But you know what, before I get started today, I'm actually want to appreciate the God Almighty, you know, for the gift of life, the love, mercy, and unmerited favor that my family and I receive. I also want to use this opportunity to appreciate the head of Department of Statistics, University of Ibadan, Nigeria, Professor Shiru. Professor Shiru supervised my doctorate degree program while in the Department of Statistics, University of Ibadan, Nigeria. Professor Shiru was my lecturer, mentor, and a father. I also want to appreciate an associate professor, Shuku, Associate Professor Angela Shoko co-supervised my PhD work. She was my lecturer, my mentor, and a special sister. Permit me to also give my appreciation to the LISA coordinator, Professor Olubusoye. Professor Olubusoye was my lecturer, my mentor, and a father. I also want to appreciate all the senior academic staff of the Department of Statistics, University of Ibadan, that nurture my statistical seed to an harvesting stage. I want to appreciate Professor Amaya, Professor Bamiduro, Professor Iyaniwura, Dr. Adepoju, and the rest of others. I want to appreciate all of them because they actually contributed significantly, okay, to my growth. I want to appreciate every member of academic staff of the Department of Statistics, University of Ibadan. I want to appreciate the fallen heroes. I want to use this opportunity. I'm so sorry, I'm going to be emotional. I want to use this opportunity to remember the fallen hero, Dr. Adelakun, Dr. Iwuno, Dr. Paid in mathematics, and I want to say, may they, rest in perfect peace. I want to appreciate the current academic staff, the non-academic staff, the LISA team, the wonderful students, the participants, ladies and gentlemen. I think I want to say I feel honored and humble to be here today. I'm so sorry that my greeting actually take forever because this is going to be the first time of speaking with my base in more than 5 years. I want to say that this is going to be the second time I'm going to give a lecture in a program powered by LISA. The first one was actually given in 2016. And you know what? I will continue to collaborate with LISA and with any organization whose priority is actually on the advancement of knowledge, particularly those who are going to be sending statistical message and data science message all over the world. Okay, let's get started. Okay, today I actually want to present a topic called machine learning and data science, a variant of statistics. Why do I choose this topic? Of course, I chose this topic because of the controversy around the topic. And today, I'm actually going to do justice to this topic, using the information available at this time. Because what is permanent in life is change, things are changing. Okay, let's get started. I'm actually going to be guided by this outline. Of course, I'm going to provide an overview. I'm going to go to definition of terms where I'm actually going to differentiate between statistics, data science, and machine learning. Of course, I'm actually going to talk about the similarity as well. And of course, in the application today, I think I'm actually going to identify some inconsistency in application of statistical analysis. So then I'm going to use what I call the variable selection, the nested model, and I'm also going to touch classification problem. Then after that, I'm going to make a conclusion. Okay, now let's get to business. When you look at the topic, of course, I said data science, machine learning and data science are variants of statistics. Why do I say variant of statistics? You're actually going to find out today. But let me start by definition. What is statistics? Okay. According to the American Statistical Association, statistics is the heart of learning from data. I'm going to say that again. Statistics is the heart of learning from data. But you know what? Because there's a professor in the University of Michigan, and which I actually cherish a lot. And he said, you know what, statistics is more than just a science. And included in the definition, he said, statistics is the art and science of learning from data. Okay, so which means statistics is more than science. Okay, let's look at data science. What do we mean by data science? The data science is actually a field of study where scientific approach is actually being used to extract insight, meaning from data. Okay, take a look at that. Then what is machine learning on the other hand? Machine learning is just a group of devices used by data scientists, okay, that enable computer to, learn from data. Take a look at the three definitions. Now, when you take a look at the three definitions, you're actually going to see that there is data in the three definitions that I just gave right now. Statistics, the art and science of learning from data, data science, okay, a field of study, okay, where scientific approach is actually being used to extract meaning, insight from data. Machine learning, two, a group of devices used by data scientists, that enable, computer to learn from data. When you look at the three definitions, they revolve themselves around data. Okay, now let me tell you this. Okay, I think I saw a chat right now, somebody talking about, I think that is exclusive to Lisa. I want to believe at the end of the day, after the talk, I can actually attend to question if and only if that will be allowed by Lisa. Okay, like I said, the three definitions actually revolve around learning from data. Now the question now is, how do we find ourselves in this kind of situation whereby one way or the other, we got to learn from data? Now, take a look at this. We live in a world, okay, where that is full of variations. Different things happen in different days. Okay, then I'm going to say because of that, we live in a stochastic environment. Okay, we live in a stochastic environment because the existence of reality is independent of human knowledge. I'm going to say that again. The existence of reality is independent of human knowledge. Okay, and you know what? In addition, we got variations in the world. Okay, and because of that, it makes the world to have more than one state of nature. Okay, now the question is, how do we, we need to understand our environment. I want to understand my political environment. I want to understand my economic environment. I want to understand my financial environment. I want to understand my psychological environment, my sociological environment. And you know what? If I want to understand my environment, then what do I need to do? Okay, what I need to do, we need to collect data. Okay, but you know what? I think I want some people to mute because the background noise. Otherwise, I'm actually going to mute everyone. So thank you so much. Okay, we want you to mute and we don't want the background noise to disturb others. Thank you so much. Okay, when we collect data, we realize that the information that we're looking for is not readily available. Let me tell you this. The information that we need to understand the world we live in is actually embedded in data set. Okay, and you know what? It is information that we're actually going to translate to knowledge, and the knowledge that we need to, we are in the first place, we're looking for knowledge because we need knowledge to understand the world we live in. And therefore, the information in data is not readily available. Something needs to be done. Statisticians apply statistical model on data set in order to review the information in it. The data scientists use a different approach. They took the advantage of the new technology, okay? And instead of human being learning from data, of course, they make use of computer. Now, let me just tell you today, in statistics, they use statistical methodology, and in data scientists use machine learning. But before I go forward, I'm going to say this. Some of my students, they might ask me this question: why do we have variation in the world? But my response to them is that if you want to look at it from a religious point of view, or you want to look at it from a biological point of view, then from religious point of view, I'm going to say the variation in the world is actually created by God. If you look at the account of history of creation, Almighty God started variation. That is what I used to tell my students. Do you want to ask me why? Then I'm going to say the reason why God Almighty started variation, if you look at the account of creation, what he created in different days, he did not create the same thing. Okay, what he created in day 1 is different from what he created in day 2, and so on like that. It means the first sample space was created by God Almighty. And you know what? Statistics, mathematics, machine learning, manipulations in general only thrive in variation. If there is no variation, I'm so sorry, there's no statistics, there's no mathematics, there is nothing to manipulate in the world. Now, if I want to use the theory of evolution, of course, one of the evidence of evolution is mutation. And mutation has a direct link to variation. And that is the reason why we find ourselves in this kind of situation. Now, between the machine learning and statistical algorithm, I think I'm actually going to explain this. Because because of time, I think I will quickly go into the difference between the two. I'm going to use the school they come from. When do they come into existence? As such, they work on the type of data, the nomenclatures, and so on. Before I move ahead, I just want to confirm again. Are you guys still hearing me clearly?
Yes, we can hear you, Doctor. Very well.
Okay.
Very clearly.
Thank you so much. Thank you so much. But I need to confirm that. Yeah, thank you. Okay, let me start from this. The difference between machine learning and statistics. The school they come from. I want to tell you, statistics have been here for centuries. In fact, the age of the art, I told you, Almighty God started statistics with the event of creations because he was the first person that curated a sample space. Okay? And the event of creations are mutually exclusive and mutually exhaustive. Okay, but when you look at data science, the data science actually started in the 90s. Okay, so, but let me tell you this. I'm going to say this. Statistics was primarily designed, okay, for in the pre-computer era, to handle the data problem in the pre-computer era. I'm going to say that again. Statistics was primarily designed to figure out data problem in pre-computer era. Statistics actually, then when it was designed to test the effect of fertilizers in the field of agriculture. Generally speaking, I'm going to say statistics is made for small samples. Some of you will want to argue that with me, that what about central limit theorem? Okay, I'm aware of central limit theorem, but you know the central limit theorem have a threshold. What was the threshold? The threshold for a sufficiently large sample in the central limit theorem, put it at 30. I'm going to write that down. You know, when the sample size have a threshold of 30, look at that. That is that. But you know what? We find ourselves in a world where things are changing. You know, the way data set are being produced, the data set, there's a data, evolution. I think I actually want, okay, maybe I'm going to mute because people are really disturbing. Okay, please, I want you guys to mute. Okay, because of the background noise. Thank you so much. I want you guys to mute. Thank you so much. Okay, what I'm trying to talk about is this. You know, do you know that billions of data are being produced? And you know what? Statistical methodology cannot handle big data. I'm going to tell you why. And let me tell you, within the last 4 years, 90% of data set in the world was produced. With the evolution of Facebook, Instagram, and social network, there's a way, you know, we generate data set every second, every minute, every day. Okay. And you know what? Statisticians, you know, influential statisticians, they've really recognized, they acknowledge the fact that statistical methodology, you know, fail in situation where you want to handle billions and trillions of data set. Okay, and I'm going to demonstrate that to you today. Then another thing is assumptions. Oh my God, statistics has a lot of assumptions. Okay, insurmountable assumptions. For instance, you want to look at relationship between variables. Particularly, you want to fit regression model. You're going to be talking about assumption of normality, assumption of constant variance, independence, and so on like that. You're going to talk about whether outlier is present, what about high leverage, and so there's a lot of assumptions. And that is not making statistics to be attractive to the industrial world. Okay, but when you look at the machine learning, on the other hand, there is assumption, but the assumption is very, very little. Okay, and let me talk about lucrativity. I want to tell you, according to you know, a Google search engine, a job search engine, Indeed.com. Okay, Indeed.com actually the data on Indeed.com shows that but before 2011, hardly will you see a demand, you know, a job demand for data scientists. But you know what? In 2015, the demand for data scientists have really surpassed the demand of statisticians. Now I'm gonna say something again. If you go according to the data available on the Glassdoor, okay, another job search engine, the salary, the average annual household, you know, I mean, the average salary, annual salary income for a statistician in the United States is $75,000 US. But you know what? The data scientists, on average, they earn about $120,000 US. The difference is clear. So why is it that the industries, you know, they are actually demanding for data scientists more than the statisticians? I'm going to tell you, you know, one of the reasons is just that there's a lot of assumptions in statistics. A friend of mine at the University of Minnesota tell me one time, she said, there's a lot of assumption in statistics. He said, according to him, nature does not assume anything before the occurrence of universe. Give me 1 second. I think I want to see whether I can mute people from here. Give me 1 second. Because people are really disturbing.
Citizen. Which bus is it?
Okay, I think I've muted everyone. I want to confirm, can you guys hear me clearly?
Yes, we can hear you clearly.
We can still hear you.
Okay, you know, you can only unmute yourself if you, that would be the end of the, I mean, at the end of the lecture. Please, I want to beg everyone. Okay, the background noise is actually disturbing. Thank you so much. I'm actually going to go back to my slide. Okay, now, let me tell you this. In terms of, let me first tell you how statistical model work and how machine learning model work before I go into application. Statistical model, we start from the specification of model. Okay, we're going to start from specification of model. It means what actually produce that model specification is our thoughts. You know why? Our thoughts could be wrong, which means we're going subjective. Okay, now after the specification of the model, what we're actually going to do, we actually going to, because the model we are actually specifying, we have a what I call a random component, which is what we call noise. Then there's going to be a lot of assumptions around the noise. And in the end, when you are trying to validate the model, you, after estimating parameters and you know, when you're trying to validate the model, I want to believe you're actually going to use residual analysis. At the same time, you're going to use goodness of fit. But I want to tell you this. According to a professor of statistics and a professor of computer science from Purdue University, the person of William Cleveland. William Cleveland is one of the father of residual analysis. William Cleveland admitted and acknowledged the fact that you know, residual analysis and the goodness of fit could be misleading. And he said it is only appropriate for situations where the numbers of predictors, I mean the numbers of independent variable, is not more than 3. Situations where the numbers of predictors is more than 3, of course, you will expect the inconsistency in the behavior of the goodness of fit. And let me tell you this. Some of you may want to argue this with me, but you know what? I'm a statistician to the core. I really understand. Do you know why? Because when you look at the goodness of fit test, the goodness of fit test, you know, some of you may want to say, okay, we have a criteria for model fitness and we have criteria for model fitness and model complexity. But you know what? I know, even though when we consider criteria for model fitness, which is the residual sum of square and the R square, I know there's a problem with that. I know statistician, we want to consider criteria that put into consideration model fitness and model complexity, which is the AIC, the BIC, and the adjusted R square. But you know what? What I'm going to show you today, I'm actually going to show you, you cannot trust your AIC. You cannot trust your BIC. That's what I'm going to tell you today. I'm going to show you today. Okay, now, I think what has happened, what I say is that the way things are changing, I think, you know, the data scientists actually outsmarted the statistician. You know what they do? When they realize that data sets are being produced in large quantity, okay, from year to year, what data scientists actually did is they borrowed knowledge from statistics. They joined that with the machine learning, with the database management. Okay, now let me tell you this. The knowledge from statistics with the computer and the database management, that gives them machine learning. But unfortunately, statistics has not really reacted significantly, okay, to new technology. Instead, the statistics continue to emphasize on theory, introductory courses, testing of hypotheses, rather than focusing on statistical computing. Okay, now I will quickly go straight. I think I put some naming conventions right here, how they work, but you know what, because of my time, I'm still going to make this material available to everyone. But before I seriously go into application, give me 1 second. I think I'm going to have give me 1 second. Okay, now before I'm going to go into applications right now, I will quickly talk about how machine learning work. In machine, the difference between machine learning and statistics is this. If you want to look at it from methodological point of view, in statistics, we specify a model, okay, model specification on data, and in such a way that we're actually going to have a dependent variable as a function of individual and parameters and the noise. But in machine learning, what we do, we don't specify any function. The function is unknown. The machine is actually going to learn whatever function the data is going to take. Therefore, the function is unknown. Then the algorithm, the function is algorithm that actually, that operates on an input variable that we can use to predict an output variable. And one of the reasons why industries actually, employ data scientists more than statisticians is because they want results. They want accuracy, predictive accuracy. That is what they want. And when you have a pool of data, big data, for instance, of course, the machine, the computer will take an advantage of that and learn from data instead of human being doing the job. Of course, don't forget, there is a limit to the capacity, in terms of brain for human being. So which means in machine learning, human effort is not that involved. But for statistics, I want to tell you, human effort is greatly involved. Okay, I quickly want to move. Then another thing I'm going to say before I go into application, I want to say this. Statistics rely on probability space. And why probability space? Is because the probability space contains the sample space, event, and their corresponding probability. I told you, Almighty God started statistics because he created the first sample space. Okay, and if you look at the event of creation, you're going to see what he created in the first day is an event. What is created in the second day is an event. Okay, and every event we have their corresponding probability. Okay, now I'm going to go into an application right now. Now let me prepare our mind. I want to go into an application right now, and I want to start with this variable selection. How do statisticians, how do they normally address issue that has to do with variable selection? And I'm actually going to show you how data scientists will approach that as well. Now, let me tell you this. Let me first tell you this. When you look at Gauss-Markov theorem, okay, where you are trying to look at the relationship between variables, we have an assumption. What is the assumption? Assumption is that the sample must be greater than the numbers of variables in a situation. I'm trying to talk about this. I don't know whether you can see what I'm writing right now. According to Gauss-Markov model, y equal x beta plus error. Okay, when you take a look at this model, the assumption in this model is that the numbers of observation should be greater than the numbers of variables. In a situation where the numbers of observation is less than the numbers of variables, the classical method cannot be used. Though Judge Box in 1986 actually provided a way out, he suggested a way out. And one of the way out is that, okay, if we can sparse the model sparsity. And sparsity the model, he said we can do up subset selection, we can do stepwise regression, we can do ridge regression, we can do lasso regression. But you know what? I'm going to tell you there's an issue with a stepwise regression, because the stepwise regression will mix the best model. And that is one of the reasons why statistics is not that attractive to industrialists. Now, what I'm trying to tell you right now, we cannot do without, in this kind of, with the world that we find ourselves in, we normally have a situation whereby the number of variables will be more than the numbers of observation. I'm going to give you an example. Microarray data. I'm talking about gene expression, where the numbers of genes will actually be more than the numbers of patients. What about the financial data, where the prices, okay, will even be more than the numbers of time points? I can remember when I was in school, when we're doing time series, we always have one particular data point recorded over time. But now I want to tell you, because of the fact that we have changes, okay, in a particular time point, you're going to have more than, if not possible, like 10,000 data within a particular time frame. Okay, so take a look at this right now. I want to demonstrate all subset selection in the variable selection, and I'm going to point out the inconsistency of statistical analysis. Now, take a look at this. You are proposing 3 predictors. These are my predictors. Okay, you want to look at the contribution of that to the response. If you want to look at the contribution of that to the response, okay, now you need to consider what is a possible numbers of models am I going to have. If you take a look at the first one, this is a complicated model where I'm actually going to have every all the predators, okay, and the simplest form of the model is the intercept, the one without predictor. Okay, now if I want to do that, then I'm actually going to use what I call the power of a set. Okay, what is the power of a set? How many subsets can I have in a given set? So if you take a look at this, I'm going to use 2 raised to the power k minus 1, where k actually represent the numbers of regressors. Okay, right now in the complicated model, the numbers of regressors is 4. Okay, when I want to say regressors, I mean you're going to look at 1, 2, 3, 4. We have 4 regressors, but we have 3 predictors. Okay, now if I want to consider, up subset, I'm actually going to have 2 raised to the power k minus 1, and in this situation, my k is 4, and that is going to be 2 raised to the power 4 minus 1, and that will be 2 raised to the power 3, and that is going to be 8. It means the possible numbers of models I'm actually going to consider is going to be 1, 2, 3, 4, 5, 6, 7, 8. But you know what? It is only one model that will be that will be the best among these 8 models. Okay, now if I based on what Judge Bell suggested in 1986, okay, I'm actually going to show you using stepwise regression. I'm going to show you right now, if you want to do that, you can go backward, we can go forward, we can go both directions. But you know what? If I want to do the backward elimination or forward selection, I'm actually going to consider the criteria that consider model fitness and model complexity. Okay, the criteria that I consider model fitness and model complexity is actually either I consider backward elimination with AIC, or backward elimination with BIC, or backward elimination with adjusted R squared. But what I want to show you right now, I'm actually going to show you how backward elimination with AIC work. If I were to do backward elimination with AIC, I'm actually going to start from the complicated model. Okay, the complicated model is the one that have all the predictors. Then I'm going to obtain the AIC. The AIC is -112. And after that, what I'm going to do, if you take a look at this, I started from here. How many predictors do I have? I got 3 predictors right here. And I'm going to go, I'm actually going to consider, go for possible 2 predictors. I want to see, instead of me to use the 3 predictors in this model, if I use 2 predictors, is the model going to be improved upon? Now take a look at that. Because of that, I consider the step 1. If you take a look at step 1 right now, I'm actually going to consider when I have 2 predictors. Okay, when I have 2 predictors, I computed the AIC. When you look at the AIC of the complicated model is actually -112. Then in the step 1, I'm actually want to consider whether instead of wasting my weapons in my statistical arsenal, I want to see whether if I only consider 2 variables, whether I'm actually going to be fine. Okay, if you take a look at what I have, the possible 2 variable x1 and s2, x2 and s3, x1 and s3. If you take a look at that, we computed the AIC, and you know what? In the end, you're actually going to see that this guy here is the one that is less than, than the AIC over there. So which means, even though this one is also less, okay, but this is a bad, this one is bad because the AIC there is actually greater than the start where we started from. And of course, I'm actually going to choose this guy. Why am I choosing this guy? I'm actually choosing this guy because he's the lowest when I compare this guy with this guy here. Okay, now after that, the next thing that I'm actually going to do is right now, up to step 1, the best model is actually this guy here. Now, if that guy is the best model right now, then we actually want to see whether that model can also be improved upon. You remember the other time I said we consider 3 predictors right here, 2 predictors right here, and the next thing is actually going to be 1 predictor. And you know what is actually going to give me the sense of what I'm going to use? Okay, if you take a look at this, I got x1, I got x3. Then because of that, I'm actually going to consider a simple linear regression model that have only x1 in it and has x3 in it. And if you take a look at what I have right now, we're actually looking for a model that will improve on -119. And if you take a look at what I have right now, you're actually going to see that this guy here is less than -119. Take a look at that. So which means if it is less than -119, then what am I really talking about? What I'm talking about is that the best model that we have chosen according to the backward elimination with the AIC is actually this guy here. Okay, that is the best model that we have chosen according to the AIC. Now, according to backward elimination with AIC. But if I want to go forward, if I decide I want to go forward, then I'm going to tell you one of the inconsistency in statistical methodology right now, because what I'm actually going to settle for the forward selection with the AIC will be different from this model. You're going to see that right now. Okay, I'm going to show you. Now, take a look at, okay, this is what we got for the backward elimination with the AIC. Give me 1 second. Okay, let me see the forward. Did I put it forward? I just wanted to see what is going to happen with it forward. Okay, this is backward. Just want to see, did I put forward? Okay, this is backward. Okay, now when I did forward, I got a different model, doing forward. And the model for forward actually choose this guy here. Okay, the model for forward that I did actually choose this guy here. But the model for backward that I did choose this guy here. But you know what? If you take a look at it means when I use backward, then there's possibility, the model, the method the model will actually miss the model with the lowest AIC. Okay. So that is the reason you can see right now there's a conflict of interest. Okay. Now, I want to go into application right now. And the application is this. Let me tell you this. The machine learning can actually be, you can use an R software for machine learning, but the majority of data scientists use Python. Oh my God. I think I'm going to give me 1 second. I'm actually going to mute again. I'm going to mute again. Please, I want to, I'm making an appeal right now. Okay. I want people to mute. Okay. Please. Thank you so much. Please mute. When I muted some people, but they are mute again. Please mute. Please. Please. Okay. Let me see what I can also do again from here. Yeah, I think I've succeeded in muting everyone. Please, I'm appealing to everyone to please mute. Okay, please mute. I've already muted everyone. Please don't unmute, please. Okay, now, I want to use this as an example right here. In this example, want to look at the effects of the amount spent advertising on YouTube, advertising on Facebook, and advertising, how does that really affect the sales? Okay. Now I'm going to use our statistical approach, and I'm also going to use the machine learning approach. Now, let me tell you, in the machine learning approach, right now, the code that I wrote here is I'm doing machine learning in R. Like I said, you can do machine learning in R. You can do machine learning in Python, but only that more than 95% of data scientists use Python because Python has powerful scientific packages that are compatible with machine learning. Okay, now what I'm actually going to do here, I want to compare two models. And the two models is actually model with interaction, model without interaction. I want to look at the effects of, the amount we spend advertising on Facebook, the amount we spend advertising on YouTube, on the sales. And we're going to consider a model that will allow interaction. Okay. And in statistics, we call this nested regression. Okay, the simple model is actually nested in the complicated model. Now, what we do in data science, we're actually going to partition the set of data into two. We're going to have a training set. We're going to have a text set. Okay, but you know what? for the training set, we're actually going to use, we can use between 5 to 30% for training. But what I'm doing right now, I want to use 80% of my data set for training. Okay, so if you look at what I've curated right now, I got a trained data, I got a test data. The difference between data science and statistics is that in data science, they're going to split their data into two. And you know what, if they are after estimating, after the computer learn from, from the trained data, then they're going to use the test data for validation. But what we do in statistics, we don't do that. What we do in statistics, after evaluating our parameters in our model, what we do is to evaluate our model using residual analysis and goodness of fit. That's exactly, of fit test. That's exactly what we did. Okay, now I wanted to take a look at this right now. Oh my God, doing this in R, if you look at the one right now, model one is, is the model without interaction. I'm looking at the effect of the amount I spend on YouTube, amount I spend on Facebook. Okay, I'm looking at the effect, their respective effect, the main effect on sales. And if you take a look at this, that's a trained data. Okay, I said I'm actually going to partition my data set into two. I'm using a trained data right now. Okay, in the end, if you take a look at what we got, okay, this is the output. But you know what, data scientists don't care about the p-value, they don't care about the estimate, they don't care about the standard error, they don't care about the t-value. What do they care about? I'm going to tell you right now, okay, the validation they do in data science, what they're going to do, the data science, they are targeting accurate prediction. And what they're actually going to do, they're actually going to use it. You can see the test data right here. They're going to use the test data to evaluate the model by trying to obtain the prediction error. Okay, they're going to get prediction error. They're going to get the RMSE and the like. Now, when you take a look at this, this is the RMSE, okay, for that particular model, and this is the R squared for that particular model. Okay, this are what they actually computed, for this model right here. Okay, for the model right here. This is model one. Now, if you now compare, look at another model right now. Model two is a model with interaction. Okay, if you take a look at what I have right now in model two, I did not only have main effects, I also have the interaction as well. Take a look at that. Okay, so which means model one is actually nested in model two. Okay, how do we do this in machine learning? Okay, what we're going to do in machine learning, we're actually going to train our data set again. And when we train our data set, what we're going to do, we're going to have this regression, this output. But like I said, machine learning, data scientists don't care about that. We don't care about the estimate. We don't care about standard error. We don't care about p-value, because data science is not meant for interpretability. It's only meant for predictive accuracy. But when you want to talk about interpretability, yeah, you talk about statistics. And that is the reason why statistics can never go on extinction. Statistics is still going to be, because one of the limitations in data science, okay, if you're looking for interpretability, you can, using machine learning, of course, you are not going to get a good result. You can't interpret. But when you want to talk about interpretation, okay, of course, we give that to statistical modeling. Okay, but if you want to talk about predictive accuracy, prediction, okay, the machine learning is what. So if you take a look at this now, they don't care about this, then it means again, they're going to recompute the RMSE, they're going to compute the R squared based on the test data, and they will now compare the RMSE and the R squared of this model with the other one for them to take their decision. That is what they do. Okay. And why is it that, why are they doing that? I'm going to show you how statisticians will address the same problem. Okay, I'm going to show you how statisticians will address the same problem. This is a problem again. I'm calling that model 3, model 4. The first one, model 3 right here, is a model without interaction. Model 4 is a model without interaction. And you know what? Before fitting any of this model, you got to make sure that all assumptions are, hold. Assumptions of linearity, assumptions of constant variance, assumptions of independence, assumptions of normality. You got to make sure there is an absence of outlier, there is no high leverage. Oh my God, those are a lot of assumptions. And that is the reason why in the Western world, they want, when a problem arrives, they want a situation whereby this problem is solved on time. They don't want a situation where they're going to get overwhelmed by the problem. And that is the reason why, in addition to our statistical knowledge, we need to acquire a data science knowledge. That doesn't mean we are going to eliminate statistics. Statistics is going to stay forever because the data scientists actually borrow from statistics. Now, if I want to compare two models that are nested, using a statistical approach, what are we going to do? Of course, we're going to use a partial F-test. What I'm doing right now is a partial F-test, okay? Because model 3 is nested in model 4, okay? And what I'm just trying to do right here, I'm just trying to see whether model with interaction will do the job against just considering main effects. But right now, the p-value right here, okay, the statistician is going to use that p-value right there, to take a decision regarding whether to reject simple model or to go for complicated model. And when you take a look at the p-value right here, of course, the p-value is less than a given level of significance. And of course, under the non-hypothesis, the simple model is fantastic. Under the alternative hypothesis, the complicated model is fantastic because of the fact that the p-value right here is less than a given level of significance. They're actually going to reject, the simple model, and they're going to conclude that if I want to, measure the effect of YouTube, the amount I spend on YouTube, amount I spend on Facebook on the sales, then I need to also consider interaction. So which means interaction right here is significant. That is the meaning. But you know what? Before statisticians will arrive at p-value equal to this, oh my God, they need to be able to satisfy so many assumptions. And you know what? As pointed by William Cleveland, a professor from Purdue University, is a professor of statistics and also a professor of computer science, and is a father of residual analysis. And he has already acknowledged the fact that residual analysis could be misleading, because when you take a look at the p-value right here, of course, we put into consideration the residual sum of square before you could get the value. Okay, and that is why it is not really attractive to them, because of the inconsistency, in statistical results. Okay, now another thing that I want to talk about right now, I've talked about variable selection. I think I put a lot of example right here. Now, if I want to do variable selection with machine learning, what am I going to do? Okay, now maybe I want to look at factors that determine the price of an iPhone. Okay, and we get a lot of variables right here. The battery power, does it have a Bluetooth or not? What about the clock speed? And so on like that. We got a lot of variables right here. Okay, now if you want to use a forward and backward, what statisticians are actually going to do, they're going to use the forward and the backward to select variables, that are relevant to the response. They could do all subset selection. They could do ridge regression. They could do lasso regression. All those regressions, they have a lot of assumptions. that are difficult to meet. Okay, and if I want to use the machine learning, the machine learning, the way it works, you don't need to specify any function. The function is unknown. As far as we're concerned, the machine is actually going to learn from data, okay? And the machine will decide on the function, not human being. This time around, that is going to decide for that, okay? Now, when I do that, this is the result that I got. Like, I'm going to make my materials, everything available to Lisa at the end of this lecture, okay? And let me also tell you this. There are some features in machine learning that statisticians have not really taken advantage of. Take a look at this picture right here. In variable selection, where you have a lot of variables, it is not all of them that are actually going to be significant. How do we eliminate, variables that are irrelevant? Because even in machine learning, if you have a lot of variables and some of them are irrelevant, it will take a long time for machine to learn, not only in statistical analysis. But you know what we do, there's some features in machine learning, that we call tree-based classifiers, like k nearest neighbor, decision trees, random forest, and so on like that. Take a look at this what I'm trying to show you right now. Oh my God, this particular analysis have already figured out those variables that are likely to be important to the response. You're actually going to see. Some of you may want to argue out this with me, that, okay, when I'm condemning statistics, when I'm identifying some inconsistency in statistics, what about PCA? What is the work of principal component analysis? I know when we have a lot of variables that are correlated, the principal component analysis can actually be used to convert correlated variables into a correlated one. But you know what? The principal component analysis has issue. It has limitation because it has an assumption. Assumptions must hold. And that is what is making people to run away. That is why it is making people to go for data science, where I don't need to do a job of thinking about the function I'm actually going to use, when the boss can actually learn from data and figure out the model, the function that I'm going to use. Take a look at that. Okay, so I put a lot of, now take a look at the correlation matrix. If you take a look at, if you really want to know, if you look at those ones that have the I value, these are the essential features you can see in machine learning. Okay, now for classification problem, I did something last week. I tried to compare logistic regression that we use in statistics with the classifiers in machine learning. Okay, but you know what I realized? When the data set, when the sample is small, okay, logistic regression can compete favorably with the classifiers in machine learning. But you know what? In a situation where I got a lot of variables, oh my God, logistic regression cannot compete favorably with machine learning classifiers. Okay, I think I've already done that. Now, which is better between statistics and data science? I'm going to tell you, within 5 years, when I was in Nigeria, I published 30 I put 30 papers. But when I get to the United States and I saw the way things are going in terms of technology, then I slowed down. I try to understand. I try to acquire data science knowledge. Let me tell you this. Data science cannot replace statistics. If you look at the suggestion of professor of statistics and professor of computer science from Purdue University, a person of William Cleveland. William Cleveland said, a field of statistics should be expanded and be renamed data science. And I said no to that. And you know what? Another professor from Columbia University in the United States of America, a person of Andrew Gemma. Andrew Gemma said statistics is a subset of data science, a less important concept. I don't agree with him. And I'm going to tell you what the Department of Statistics are doing in the United States of America is that they introduce another department called data science, because the fact remains statistics has limitation, data science also has limitation. You know, if you want to talk about big data, you use, you go for, data science. If you want to talk about small data set, you go for statistics. If you want to talk about predictive accuracy, you go for machine learning. If you want to talk about interpretability, you go for statistics. I want to give you an example right now. Let's assume that a credit card company is interested in investigating, customers attrition. What do we mean by customers attrition? Why they are losing customers to the competitor, to their competitors. In that situation, you cannot applying machine learning in that situation will not do the job, because that is a problem of interpretability, because the company actually want to know what is the contribution of some variables to the reason why customers attrition occur. But take a look at another example. Netflix, they are interested in you building a performance recommendation engine. I'm going to say that again. You want to build a performance recommendation engine. If you want to answer that question, you cannot use statistical method, because that is not a question on interpretability, but that's a question on performance. Then that is actually going to be an attribute of predictive accuracy. Then in that situation, the machine learning is actually going to do the job. Okay, now in my recommendation, okay, before I finish my talk today, in my recommendation, statistics is going to stay, data science is going to stay, okay, but because of the fact that data sets are being produced in large quantity, okay, and we've seen the limitations of statistics, I think we need to also acquire the knowledge of data science. I can remember when I was doing my interview as a lecturer at the School of Statistics, University of Minnesota, I was tested not only on statistical knowledge, but on data science knowledge. Imagine if because the world is changing, we need to change with the world. And that is it. But in the future, I'm seeing two of them coming to become one entity. Okay, but you know what? In my conclusion, we need statistical knowledge. In my conclusion, we need data science knowledge. Okay, and of course, we've already identified situation. There's a lot of situation around, where the statistical approach, is appropriate, and where the data science approach also is appropriate. Hardly will you find a Department of Statistics in the United States of America without a data science program. Okay, let me see what I have more. Okay, so that is going to be the end of my talk today, and I actually want to appreciate the participants for listening. And if anybody want to ask question, I think I'm actually going to answer. Okay, thank you so much.
Oh, that was a very wonderful presentation. Thank you very much, Dr. Kazeem Adepoju. We really enjoy your talk, and it has been wonderful listening to you again. It's been long, and I actually enjoyed the talk. So I wouldn't know before any questions. What I would suggest is that if anybody has questions, you can quickly put it in the chat room so that we can take your question because we have time. Then before that, I want to welcome Professor Oyi Olubisoye, the coordinator of UI LISA, to give his remarks. Professor Olubisoye, you are welcome, sir.
Well, thank you very much. And I want to especially appreciate our lecturer for today. He's a superb lecturer, now well-refined lecturer. Yeah. And of course, he's also now teaching his lecturers, which is highly commendable. I mean,
thank you, sir.
We all pray that our children should know more than we know, and should grow, much better than we have grown in life. So I'm happy to listen to your erudite presentation. And this is the kind of thing that we want to encourage in UI LISA, that we can always support one another and help one another to grow. Now, he is not here in Nigeria physically with us, but he is also contributing to the development of statistics in Nigeria. And I thank you very much. Now I'm in your school. I hope I will also graduate, hopefully. So,
oh my God.
On that note, I want to encourage as many people to react to this lecture. It's been a very fantastic, very highly educative lecture. Thank you very much.
Thank you, sir.
Thank you so much, sir.
Okay. So if you have any question, if you cannot, if you can quickly talk, let's, Oh, Dr. Femi Ayola, it's good to see you. We are so happy to see your face.
Okay.
Oh, you have the floor, sir.
Okay. I thank you so much for giving me the privilege to talk, giving me the privilege to actually contribute. Sincerely, we are on the right way. LISA is on the right way. We are growing, and it's a privilege to have been educated in that very department. As the lecturer said, I appreciate his lecture. He has actually thrown so much light into what we know as in the area of a theory, and today is in the area of the application. Thanks to the Department of Statistics, HOD, the director, Professor Olubisoye, and my supervisor, and the lecturer of today. Generally, if we look at what he has taught us, and based on the opportunity, the privilege God has granted him, and myself, it is a privilege. When we really look at it, we go more into area of application. And in order for us to actually be able to do justice to the challenges of today, because we generate data every moment, every minute, every second, in order for us to be able to handle it, right, we need this knowledge. Yeah, we have been able to acquire, when we were there at home, we were able to acquire the theory, the theoretical part, we were able to acquire R, Excel, and so on and so forth. All those knowledge, they are premise on which we are building on. They are not write-off, they are very good knowledge, as he has said earlier. Please, I will enjoy other colleagues, our students, our senior, to actually dwell more in this lecture. And I can see it because I think sometimes about 2 years ago, departments are thinking towards this direction. Please, so many lectures are on YouTube where we can acquire all these skills. So many are on Coursera, so many on our edX, and so on and so forth. We can acquire all these skills based on our commitment. And the only way to be committed is by hearing. And the only way to be here, to have opportunity to hear, is having this kind of a platform, LISA, Department of Statistics. Thank you for good job. Thanks to the coordinator, thanks to the student, thanks to the lecturer, and everybody. Best wishes. Thank you so much.
Thank you very much, Dr. Ayola. Thank you for that remark. So do we still have anybody with question or comments?
Yes, I have a comment.
Oh, that's good. That's Mr. Ahmed Olanriwaju, our own Abolo.
Yes.
You have the floor,
Yes,
sir.
thank you so much. Yeah, I really want to. I'm really glad I was able to attend this lecture, because the fact that there's a lot of arguments when you say people fighting who owns machine learning, who owns data science, you see statisticians and computer science competing over what but I'm really glad that because I'm an active member in the community of AI, machine learning, data science in UI.
Yes.
And I'm glad that I can say conveniently now that we are beginning to have a lot of statistics students coming to join us, unlike before, that they'll complain that, oh, if you do machine learning, when we get to the department, we might have issue with defending our. But now I'm glad that with the support of the likes of Professor Lubisoye, supporting students who started doing machine learning projects in the department, standing to defend them during their presentation. I'm really, really glad that this presentation has further cleared my doubt that the statisticians are beginning to push further. That look, machine learning has not come to display statistics. Without statistics, there is no machine learning. So I'm really glad that I was able to be part of it. So thank you so much once again. Oga Femeola, well done. Just be hiding your face, so God sabi you.
Thank you very much for that. I don't know if we still have any comment or question from the participants. We still have question? Okay.
I can see Dr. Chowali raising up his hand.
Okay.
And there are a few questions on the chat. Dr. Kazeem.
Hello, Mark. Can you hear me, please?
Yes, okay. I can hear you clearly.
Thank you for the wonderful presentation. I really appreciate and I really enjoy the presentation. I have a clarification, a question, please. Concerning that example that you cited, based on the backward and forward selection, we have a problem there. So what is the solution? What is the way forward, please?
Okay.
Thank you, Mr. Presenter.
Yeah, take you to I think the way forward is just if you look at it, that is not the only area in statistics where there is a conflict of interest. I think if I want to answer your question, maybe probably if you want to say, okay, what is the way forward? If I want to answer the question within statistical framework. Now, if I don't want to answer the question within statistical framework, I'm going to say the way forward is basically you need to consider what is the purpose. What is the purpose of your research? If the purpose of your research is for predictive accuracy, you're actually going to go for machine learning. If it's for interpretability, you're going to use statistical model. Now, situation whereby there's a conflict of interest between the backward elimination and forward selection, I think what we can do with statistician, we need to revisit assumptions. I think assumptions is what makes statistical model to be rigid. Imagine a situation whereby I want to use a rigid model on the model dynamic situation. It's not going to, augur well. And that is the reason what we can do. Part of what I was doing when I was in Nigeria, I was doing what we call robust statistical modeling. What do we mean by robustness? Is there a way we can actually put some parameters, maybe like shape parameters into the model to make the model more flexible so that the model can actually commiserate with reality, so that we can use a flexible model for dynamic situation. So that is what I think you can do, revisiting assumptions if you are seeking redress in statistical framework. But if you don't want to seek redress in statistical framework, I want to believe there are better approach to that using machine learning. Because take a look at this. I want to travel from Chicago to New York. Chicago to New York by road is 22 hours. But Chicago to New York by flight is 2 hours. Somebody is going to tell me that, of course, we know the plane will get to Chicago before the car. But before, it's not as if vehicle will not get to Chicago, but there's going to be a lot of assumptions. Okay, is your car in good condition, the gas, and so on like that. I'm actually referring to that car as a statistical method. And I'm referring to flights now as much as the data science. You know why? Somebody's going to tell me, what about the risk? What about if the plane crash? The fact remains, 1 out of 11 million Americans died due to plane crash, while 1 out of 5,000 Americans die due to road accidents. Now compare which one is more riskier. It is the vehicle, traveling on vehicle. So if a computer can actually do my job, with the incorporated, maybe with a very little incorporation of statistical knowledge, then why do I need to go for a complex model? I don't know if I've answered your question. You're hearing me, right?
Yes, I can.
Okay.
Thank you very much.
Thank you so much. I think I want to read. I want to read my chat.
All right.
In my chat, somebody said, my comment is that in order to have a good synergy between statistics and data science, the theory of machine learning should be made clearly available so that core statisticians can easily embrace and feel at home with it. And the person said, for example, if a statistics student is presenting a research work in machine learning, it won't be appreciated by core statisticians without making those theories clear. Now, let me tell you this.
I think I know.
If you want to operate in any place, we need a constitution. You are coming into a statistics program. There is a curriculum that you actually need to fulfill. If a statistics student should use a machine learning approach, or in a department where the curriculum is around statistical models, then I'm saying that as an infringement. And what I'm actually going to recommend to the Department of Statistics is to also review their curriculum, because the statistics department can take the student up based on curriculum. They're going to tell the student, look at what we put in the curriculum. There's no machine learning in the curriculum, even though the student is trying to adapt to change, but the department is actually going to let him down. And you know what? Because of what they put in the curriculum is what they expect the students to follow. And then the only answer to that is that, I'm so sorry, the students need to follow the curriculum provisions of any of the departments. And maybe when you are out of that territory, then you can apply your machine learning in the larger society. I mean, whatever approach in the larger society, because you can be taken off for that. So that is my response to that. And the last questions here said, what are we going to do after cross-validation of machine learning model, but the best or high-performing model is not parsimonious, not feasible, or cost-effective for business implementation? What can one do? Okay, oh my God, you just touched a point right now. We have a different way to validate in machine learning. Then it depends on what you are doing. Are you into classification, or you are into prediction and stuff like that? So that depends on the purpose. Like for instance, if you're into classification, you're actually going to get the accuracy, you're going to get the precision, you're going to have an F-score, you're going to have an ROC. They also compute a lot too to validate. They don't just use one to validate. Okay? So I think the person can actually contact me. We're going to talk more about that because it's a lot of story. Okay, that is all about what I have in the, oh, okay, there's another one. How does interpretability of statistics models help in industries, as most people in industry are shifting to predictive model? Oh my God, I attended a seminar at the University of California, Berkeley. And do you know this particular question come up? Predictive ability and model fitness. There's a difference between the two. In statistics, we care about model fitness, model complexity. If I want to talk fitness, we use residual sum of squared, we use R squared, but because of the fact that when I introduce new variable into a model, whether significant or nuisance, we know the R squared is going to go up. And because of that, we also shifted to some criteria that put into consideration model fitness and model complexity, the criteria like adjusted R squared, the criteria like AIC, the criteria like BIC. Now, when you look at those criteria, they are actually for model fitness and model complexity, but you know what? I'm afraid they don't really answer question about predictive power of a model. Okay, they don't answer question about predictive power of a model. If we want to talk about predictive power of a model, oh my God, statistical model is not as accurate as machine learning. Because in machine learning, you know, the businessmen and women around the, United States, Canada, Western world, industrialized world, they actually want a situation, they want performance. They want predict what determine the price, what determine this, what determine that. They are not interested in what is the contribution of them, of the variable. They are not interested in that. But if you want to quantify what is the role played by each and every variable in a model, then we go for statistical analysis, which I call interpretability. So there's a difference between the two. And of course, that depends on purpose. The purpose is, okay, what am I looking for? Am I looking for predictive power? Or I'm looking for model fitness and model complexity? I think we need to decide between the two. And that was why I gave an example the other time. A credit card company that is interested in determining what leads to a customer's attrition. That is not a predictive question. In that very question, it's a question on interpretability. Why is it? What are the factors that lead to, why we lose customers to competitors? That is a question on interpretability. And that is not on performance. So I don't know if I've really done justice to that. I think I'm going to listen to some other questions. The one in the chat is already done.
Yes, I think because of time, we cannot go on definitely. So maybe in the next 2-3 minutes, we can ask few questions and then round up.
Hello, I think there is a question in the chat about the percentage of training data. And
oh, okay.
You can actually,
okay. My question is around 80% training data. What informed that decision? Because in the real life setting, we do go for 70% training and 30% testing. Actually, it's between 5 to 30%, 5 to 30% for tests. Okay, 5 to 30% for tests. You can decide, like the one I did, I actually use 80%. Okay, there is no the threshold is just if you are the moment you are between 5 to 30, I think you are covered. So you can choose between that. Okay, but what I know is that if the significant part of the data set is committed to training, that will be fantastic. A significant part of the data set should be committed to training. Okay, so that is that for that question.
Thank you very much. And let me quickly pass this message. The slide and the record video, the video will be on Lisa website. So we pasted the website link on the chat. So I'm going to still put it again so that you can actually access the material later. So that is my information. Thank you very much, Dr. Kazeem Adepoju. It's good to have you around. And thanks to Dr. Femi Ayola. It's good to see your face again and all our participants.
I'm so sorry. Before I go, I would like to say something. I don't know if I can say that.
Okay.
Before I go, I actually want to appreciate again everyone, every participant today, you know, for that attend my lecture, and I also want to give appreciation to every lecturer that actually contributed nurturing my seed to an harvesting stage. Those who are alive and those who are not alive, you know, my prayer is that Almighty God will continue to bless them and meet them at every point of their need. But before I go, I'm going to tell you, do not look down on anybody in life, okay? And make sure, believe in yourself. Believe that you can get things done, even though situation around what I'm doing right now is kind of difficult, but believe you're going to get things done. Keep believing, and the moment you keep believing, there's something I used to tell myself: the road to success is narrow, and everybody will like to pass through the narrow way, and going by the accommodating capacity of the road cannot contain everybody at a time. Some people will go while some will wait. Who are those that will go? Who are those that will wait? But you know what? The whole world will step aside for a man who knows where he's going. I'm going to say that again. The whole world will step aside for a man who knows where he's going. But you tell yourself today, I will continue to be in the race of success until I'm classified among the greatest in the whole world. Don't look down on yourself. Keep believing. Have the fear of God, and God will continue to bless every one of us. So bye.
So no. Hello.
Thank you,
Dr.
very
Showale.
much. Yeah.
I think Dr. Showale is raising his hand. I just saw him now. We've called you before. You have the floor, sir. Dr. Showale. You can unmute yourself, sir.
Yes.
Dr. Showale.
Yeah, good evening.
All right. Good evening, sir.
Yes, Dr. KZ, it's good to have you online.
Thank you, sir.
So I want to say big kudos to Lisa for this opportunity. And I want to plead that these sessions like this should be continued. Just like what Dr. Yola said, it is what we need so that we can interact and exchange ideas from here and there. Yeah, however, I would like Dr. Kazeem to please help me out with some clarifications. That while listening to your presentation, is it right for us to classify data science under non-parametric statistics? So that is what I want you to react with. And then the second one is that you said predictive accuracy and interpretability, they are two different issues. However, I'm of the opinion that a good model will also be predictive and at the same time be interpretable. So I want you to also react to that. Thank you.
Yeah, thank you so much, sir. And it's good to hear from you again, sir. Actually, the first question centered on whether we can actually classify data science as a class of non-parametrics. I think if I want to look at the assumption, that the assumption does not, it does not require you to know, in fact, you don't even know a function, okay, for that, I'm actually going to say yes. But I'm also going to say the non-parametric that we have, I know we have non-parametric in statistics. Then statistics has a lot, even what they have in machine learning. But the only issue with statistics is that statistics has not really responded significantly to new technology. So and that is the reason why the data scientists outsmarted statistician by trying to borrow an idea from statistics with a computer and the database management to create an highly sophisticated tools that is more attractive to a lot of people. So I think I've answered the first question. Now, in the second question, you said that a very good model, that is, I have the model fitness, everything is fine. That particular model should also be used to make prediction. Based on the research that a lot of people, some influential statisticians have already done, what makes model to be fit? What make a model to be fantastic? I think the predictive power of a statistical model rely on assumptions. And in most of the time, these assumptions are very difficult to actualize. And do you know, different statisticians will work on the same subject, they use different statistical methodology, they're actually going to get different results. That can never happen in machine learning. You know why that cannot happen in machine learning? Because the reason why different statisticians use different statistical methodology and have different results is because the model, they specify the model using the principle of subjectivism. What do we call a model? A model is actually our thoughts, the thought of how system work. That is a model. Statistics begins with the specification of model. So a different statistician will use different kind of model, and they're actually going to use goodness of features. I'm going to say, oh, my model satisfy the goodness of features. The other one is going to say, my model also, his own models also satisfy, but in the end, they get different results. But in the case of machine learning, you're going to see that that does not require stringent human efforts. The machine is, look at the word learning. It is a machine that will learn from data. You don't need to specify function. And something like that, we have more predictive ability. Even though machine learning also has its limitation of interpretability. And statistics, of course, we can actually, because you know why interpretability is fantastic with statistical model. We do a lot of work estimating parameters. Every variable has a corresponding, if you want to measure the contribution of a particular variable, you estimate the parameter, provided everything is fine, provided the variance of a particular parameter is fine, the standard error is going to be fantastic, and everything is actually going to work well, the p-value is going to be less than a given level of significance. But let me tell you, we've seen a lot of papers where statisticians actually use p-value to take decision, even though that decision does not see the light of the day, because there's a difference between statistical significance and practical significance. That is a talk for another day. So I don't know if I've answered your question, sir. about the predictive ability. That's what I'm trying to say in response is that even though if everything is fine, which I know everything cannot be fine about statistical model, it is very difficult to satisfy assumptions in statistical model. We do a lot of stuff. Some of my students here, they're going to tell me, oh my God, why am I, we're going to carry out the test of normality, carry out the test of heteroscedasticity. After we're done with that, we're going to carry out the test on the significance of individual parameter in a model. After doing that, we're going to carry out the test on the significance of the overall parameters in a model. After doing that, we're going to look at the R-square to know the degree of adequacy of a model. After looking at that, we're also going to look at whether there's an outlier and whatever. Oh my God, that is taking forever. And that is the reason, sir. I submit, yeah.
Thank you very much, sir. That was a good one. So I don't know if Prof still have anything to say. We're about to round up and close the session.
Yeah.
Prof, sir.
Yes, I think at this junction we have to end the conversation.
Yes,
I know if we have all the time, the lecturer is quite is well loaded to do justice to whatever question that we may have. So, but for the benefit of everybody, I will just summarize the presentation in this way so that we can have something to take home. One, that data science or machine learning is data-driven, while statistics is model-driven. I think that clearly brings out the distinction between data science and statistics. Data science arises because of the big data and the need to make insights and draw inferences or predict future values from the big data. Statistics, like the lecturer said, you start with model and then you now check the data to be sure the data is suitable, appropriate for that model. So in that sense, data science is data-driven. Statistics is model-driven. If you agree with me, I think we can end this discussion on that note. I want to thank everybody. This is a 1 hour with a statistician program. When we started, actually Dr. Kazeem has given a lecture, but we used to have it in person. But now, I think it's now going international. In fact, it's worldwide now. So 1 hour with a statistician is unique to UI LISA. There is no program of this kind anywhere in the world. And therefore, those of us who are participating, you are welcome if you have anything to share with us. Just send email to me and we will give you the platform to share your knowledge with us. And we will appreciate. Our goal as a lab is to build statistics and data science capacity in Nigeria. And that is why we have developed quite a number of programs, including this one, to be able to achieve that. I thank you all. I appreciate all of you. I also thank my very able lieutenants, Dr. Olorun Sherifat, Bosa. Bosa is from Uganda and he's been working with us. He's not even a statistician, but we've turned him to a statistician. He came to UI to study energy economics, but he's going back with certificate in energy economics and also a pack full of knowledge in statistics. So that's what we do. We do not discriminate. In fact, we like to have, like the lecturer said, we want our lab to enjoy high degree of variability. Thank you very much, and look forward to having you during another round of this session. Regards to everybody. Thank you, thank you, thank you.
Thank you, sir.
Thank you, everyone. Bye-bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye-bye. Dr. Ayola.
Bye.
Bye.
Okay.
Bye-bye. Thank you.
Adepoju.
Yeah.
Alaja, Dr. KZ, thank you very much, sir.
Thank you too. Thank you so much.
Thank you very much.
Thank you. Thank you. Thank you.
Bye-bye.
Thank you, sir.
You are most welcome.
Yola, Dr. KZ, ẹ kújọ́ mẹ́ta.
Ọjọ́ kan pẹ̀lú máa.
Ẹ ti kájọ wá sí Nàìjíríà.
Wọ́n gbàgbé wa o, ẹ ti rí wọn.
Ọlọ́run ò ní gbàgbé anybody wa máa.
Ìyá bàbá Ọlábàtà ni o.
Ẹ ṣe pátá ẹ̀ jẹ́ ká gbóhùn gbogbo yín lénìí.
Adúpẹ́ fọlọ́. It's good to see them.
Yes, well done. Ẹ kú iṣẹ́ o.
Ẹ ṣé gan ma.
Thank you, ma.